In this video, we're going to use logarithmic differentiation to find the derivative dy over dx of these two functions. Now for the first one, you can use the product rule. It's not too bad, a little messy, but not too bad. But for number two, you have a fraction, a product in the numerator, a radical in the denominator. So this one, you would have to use the quotient rule and the product rule, and it will get messy. Now what we're going to do here with logarithmic differentiation, we use properties of logs. Here are the main properties. The ones we're going to use, this one here, the log of mn to base a is equal to the sum of the logs. It's a lot easier to take the derivative of a sum than it is a product. So we can take a product and write it in terms of sum of logs. Same way with division. It's easier to take the derivative of a difference than it is a quotient. So the main properties we'll be using will be this property here, the log of mn to base a is equal to the log of m to base a plus the log of n to base a. And also the one involving the log of a fraction is equal to the log of the numerator minus the log of the denominator. And I think we'll also use this one here, the log of m to the r to base a is equal to r times the product of log m to base a. So we can rewrite it that way. So this is going to start for number one by taking the natural log. You can use other bases, base a or base 10, base e, base 7, whatever you want to do. But the most convenient way is to take the natural log to base. Well, natural log is base e. So we take the natural log of both sides. Natural log, this will be x. The square root of x squared minus 1. And then I rewrite it this way then, natural log of y. So let's treat this as a product. So the right side has the natural log of a product x and the square root of x squared minus 1. So this can be written then as a sum. So it'd be the natural log of x and then product, so this will be a plus then. And then it'd be the natural log of the square root of x squared minus 1. So I'd have the square root of x squared minus 1. But remember, that's x squared minus 1 to the 1/2. So let's just save a step here. This again will be x squared minus 1 to the 1/2. The same thing as square root. I'm going to bring that exponent to the front. And then this would be x squared minus 1. And now I just take the derivative of both sides here with respect to x. Now here we have to treat y as a function of x. So we have to use like implicit differentiation. So it would be the same formula you would use for a derivative of natural log. The argument goes to the denominator. And then in the numerator, you have the derivative of the argument, which would be y prime. And y prime, remember, is the same thing as the shortcut for an abbreviation for dy over dx. And at the right side, we simply take the derivative of each expression. So here it's natural log, so the same formula. The x goes to the denominator, and it's the derivative of the x. This will be 1 plus the 1/2 is constant, so we can just write it out. And the derivative of ln of x squared minus 1, again, same sort of thing. The argument x squared minus 1 goes to the denominator, and then in the numerator we take the derivative of that same argument. So x squared minus 1 has a derivative of 2x. So this is equal to 1 over x here. 1/2 cancels this 2 here, so this will be plus x over x squared minus 1. Then here I'm going to multiply it through by numerator by x squared minus 1 here, and the denominator by x squared minus 1 to get the same denominator. And this one here multiplied by x squared, or by x I should say. So this one by x. Same denominator now, x and x squared minus 1. So this will be x squared minus 1. How does this combine? X squared. This was x squared minus 1, so this will be 2x squared. So this is what we have so far. Took the derivative, then we simplified, and then we're going to multiply both sides by y here. Because remember, we're solving for dy over dx. We got a y in the denominator. So if I multiply both sides by y, this one will cancel out here. This will cancel. That'll give me y prime there. But remember, the y is x times the square root of x squared. So instead of putting a y over here, I'm going to put what y represents, and it represents x, the square root of x squared minus 1. Then we simplify this. This x and this x will cancel, and this is x squared minus 1. That's to the 1/2, remember, square root means to the 1/2 power. This is x squared minus 1 to the 1/2 power. So we can simplify that and write it as 2x squared, numerator, minus 1. And again, look at this, to the 1/2 power, x squared minus 1 to the 1/2 power. and then this x squared minus 1 to the first power. So subtract the exponents there, and that gives me x squared minus 1. Square root of x squared minus 1 in the denominator is to the 1/2 power. I just write it as a radical square root of x squared minus 1. So final answer then for this one, dy over dx y prime is equal to 2x squared minus 1 over the square root of x squared minus 1. That's the answer for the first one. Now for the second one, a little bit more involved, more expressions involved in this one, but we take the natural log of both sides. And this, to simplify this a little bit, I'll start it right here. So take the natural log here and the natural log here, instead of having to write the whole thing here. So then ln of y then is equal to, then on the right side, so it's the natural log of all of this. So just to shorten this a little bit, using the properties of log here, haven't taken the derivative yet. So properties of logs allow me to write this expression on the right side as the log of a numerator minus the log of the denominator. So this will be, if I break this up, it's the natural log of what I have in the numerator. But then that's a product. That's going to be a product. So that's going to break up this way. It'll be the natural log then. This part right here is a product here. That can be written as a sum. So the first one here will be the natural log of x minus 2 to the second power. But property of logs allows me to bring that exponent to the front as a coefficient. And this will be x minus 2. And then it's plus the natural log of x cubed minus 4. Okay? So again, natural log of the numerator allows me then properties of logs to break it down this way. And because I had initially a quotient, this is going to be minus the natural log of the denominator. So I could put here cube root of x squared plus 1. But that, remember, is to the 1/3 power. So I have a property that allows me to bring that exponent as a coefficient. And then this will be natural log x squared plus 1. So again, I'm taking the natural log of the numerator. But because that's a product, it allows me to break that down into a sum of logs. And this too, of course, is the exponent that became a coefficient. And because I have a fraction, that's why I get this minus here. Minus the natural log of the denominator. But this was x squared plus 1 to the cube root to 1/3 power. All I did was bring that to the front. Now I can take the derivative of both sides with respect to x. So this is again natural log of y. So treat this as a function of y. So the derivative of that would be y goes to the denominator, and in the numerator I have the derivative of the argument. So this would be y prime, which is dy over dx. Now on the right side, we just simply use the formula for the derivative of a natural log. This is just, again, derivative of ln of u. Whatever u is to the denominator, then u prime, you have it. So the derivative of a natural log of u goes in the bottom, and then in the numerator, whatever the derivative of u is. Now for this one here, it's x minus 2. So this is your u, so that goes in the denominator, x minus 2. And the derivative of u is 1, but you have the constant here, that'll be 2. Plus, same thing, natural log of x cubed minus 4. In the denominator, you put the argument, x to the third minus 4. And the derivative of x cubed minus 4 is 3x squared. Then it's minus, same thing for this one. The u in this case would be x squared minus x squared plus 1. So that goes in the denominator. In the numerator is the derivative of x squared plus 1, which is 2x. And then you have this 1/3 here, so that 3 multiplies the denominator. So you could rewrite this if you want as 2 over x minus 2 plus 3x squared over x cubed minus 4 minus 2x over 3x squared plus 3 if you multiply that out. And I put this in parentheses like this. Remember, we're solving for y prime or dy dx. So all we do here is we multiply both sides by y, and this by y, and this y, and this y will cancel out, leaving you with y prime. So this is now y prime, or if you chose to write the whole thing down and not abbreviate, this will be dy over dx. So this is your answer then. 2 over x minus 2 plus 3x squared over x squared, x cubed minus 4 minus 2x over 3x squared plus 3, y. But what is y? Why is that? So let's just replace it. Say this is x, the square root of x squared minus 1. And this is your answer. I wouldn't even bother trying to combine this, find a common denominator, especially if you're taking a test. I would just leave it like this. We got 2 over x minus 2 plus 3x squared over x cubed minus 4 minus 2x over 3x squared plus 3 multiplied by x, square root of x squared minus 1. And I take it back here. This is y, but this is for problem 1. Okay, so for problem 2, this is y. So I'm just going to write it in this way. This expression here is multiplied by that, which is of course the y. I don't have room here to put it down, so it's just going to be, this expression here is multiplied by x minus 2 squared times x cubed minus 4 over the cube root of x squared plus 1. Hope you can follow that. Thanks for watching. We'll see you next time.